Hello, good morning, good afternoon, and good evening. On behalf of PioPetro and Millet Research Hub, I'd like to welcome you all in our summer internship program. I am Mayar Tare, Senior Gas and Petrochemicals Engineering student, and I'll be your moderator for today. So before we start, please keep the chat box professional and ethical, and don't forget to drop your questions in the Q&A section below. Now, without further ado, let's welcome Dr. Rami, who will give us a session on the machine learning.
Welcome back to the second week of our machine learning course. For today, as you remember, last week we our plan was to actually focus on the challenge for the machine learning, the onward, and the great opportunities that this brings. But also, it's interesting to cover some other parts that or some of the feedback that we got, like the three main questions or the three main inquiries that I got regarding the use of the machine learning in the oil and gas industry was regarding the regulations, will hit a choke, and also on the analysis for the piping system and the pipe failure. So we will quickly have these three case studies. So we will have start with some core concepts of machine learning, like supervised, unsupervised, and a little bit get more technical with machine learning, and then cover some case studies. Uh, um, get these studies for the actual three cases that I just mentioned, and then we will have go back to the onward and discuss the hands-on challenge that as we planned last time, basically. So let's start with the core machine learning concepts and how machine learning works. So as we planned, we have the training data. This is how we tell the machine what it needs to learn, what it should learn. So this is what we call the training data, and this training data goes into the machine learning algorithm. Again, there are multiple types of algorithms, and each type has a different way to it works and different objectives. What kind of problem we should use this machine learning algorithm with. So this is the second step, that we take the training data and supply it to the machine learning algorithm for training, and then we have the model input data, because every algorithm or every model has different characters, different attributes, different input data that it needs. It needs the training data, but it also needs other data, like the how it will converge, some parameters. It's different from algorithm to another. Like if you are random forest, you need to specify a lot of the rules for how to specify this forest. If you are like support vector machine, like every machine learning algorithm has different methodology and different requirements for the model to be able to train. So this is what we call the model input data. And then we execute the machine learning algorithm. We have what we build, or what we call we fit the machine learning algorithm, and we have the model ready. So once we have this model, we start to use it for prediction, right? This is the whole idea, that the model now has learned. This yellow track is the model learning. This is the training data. The model got trained, it learned, and now we have a model ready for us to actually start using. And to use this model, what we do the process called prediction or inference. So we give the model some new input data that the model didn't see before, and we ask the model, what do you think of this data? If this is like we will identify the different types of problems shortly, and then the model gives us prediction. If the prediction, and then we evaluate the accuracy. If the model is accurate, or the accuracy is acceptable, then we have a successful model. We are happy with this model and we can start using it. If it's unacceptable, or that we believe the model still didn't learn enough to the level that we we would love to see, then we will assign this an unacceptable and go back through the training process to keep improving the model performance. So this is the general workflow of how, and this is what we covered last time when we said the typical steps. So this is another graphical way of looking into it, and maybe a little bit easier to memorize and understand. So this is the actual how it works. But when it comes to the types, what are the types of machine learning algorithms? We have four main types. We have what we call supervised learning, we have unsupervised learning, we have the semi-supervised learning, and finally we have the reinforcement learning. Typically, what we'll be working with is these two types, like supervised and unsupervised. The semi-supervised is very straightforward. It's just a combination or a mix between the two. Supervised meaning we tell the model everything. Unsupervised meaning we just give the model the data and see what the model can figure out on its own. But then the semi-supervised is both. Like we give the model a little bit of label data or learning data, but also a lot of the data that just to throw it at the model and see how it performs. And then we will talk a little bit about the reinforcement learning. So let's start with the first type, the supervised machine learning strategy or type to the supervised machine learning. So the whole idea, you can just read this straight out. It's where the machine learned on labeled dataset. The word labeled dataset is the core or the main keyword here. Labeled dataset means that you give the model the data and tells the model what is this. The very simple example is like we have the like dogs and cat photos. This is a very famous and very simple concept to understand. You have a bunch of photos of dogs and bunch of photos for cats, and you give these training data to the model and you tell the model explicitly, this is a photo of a cat, this is a photo of a cat, this is a photo of a cat. Different cats, different colors, different angles, different ages, but they are all photos of cats, and you tell the model these are photos of cats. And you do the same thing with the dogs. You have hundreds of photos for dogs, different breeds, different colors, ages, and so on. And then you tell the model these all are photos of dogs. So this is what we call label dataset. You identify every photo, what this photo is specifically, and you give the model to train and really learn what makes a photo of a cat and what identifies a photo of a dog, and then the model gives learning. So the label dataset specifies what is the input. It's the photo of a cat or a dog, and the output is this text. The model tells me, okay, this is a photo of a dog, this is a photo of a cat. So the machine is trained with the input corresponding output, and this is able to predict. So in the future, I can just give the model a new photo, and then the model tells me, okay, this is a photo of a dog or a photo of a cat. So this is the general, like one example, and this is the general umbrella of supervised, that we have the data and we have what this data represents. And using this concept, there are two famous categories under the supervised machine learning, which we call classification problem and regression problem. So these are some of the problems that we can solve using supervised machine learning strategy. The classification is basically algorithm that address classification. So again, the same word that we said, this is a cat, this is a dog, this is a classification problem. Or maybe if we use the machine learning in for an email classification, so we want to classify the email as a spam or not spam, right? And this is where we can utilize the machine learning in a real world to so we give the model a lot of emails, so many emails that are legit non-spam emails, and we tell the model this is an email, it's not spam, this is an email, it's not spam, and so on. And the same for spam. We give the model a lot of spam emails and they'll tell the model this is spam, this is spam, this is spam. So it's a data set, we label it, we tell the model what this data contains, and explain the data to the model, and then we hope the model in the future, when you give it a new email, the model will figure out on its own if this is a spam or not a spam, or if this is a photo of a cat or dog, and so on. So this is the first type of problems that we can solve using a supervised machine learning approach. Now, the second type is regression. When it comes to regression, is the model handle problems where they want to figure out a relationship between two variables, and usually the relationship could be a linear relationship, but it's not necessary. But the one of the very famous examples, like weather prediction, right? You wanna, because you are not classifying something. Somebody can say, okay, the weather is like, is it rainy or not rainy, right? But that's, so it's a classification problem. But actually, no, because when it comes to regression, you have multiple strategies. You want to predict the weather, like the temperature, like is it 70, is it 75, is it 72, 71, 80? Of course, I'm doing Fahrenheit, so don't freak out. Or you want to take the humidity. Is it 80? Is it 81? Is it 80.2? Is it 80.5? So it's not just two things you want to classify between, but actually it's a range of numbers, and you want to know the next number. Like the temperature was 75 yesterday, 79 tomorrow, and then, or the day before, 80 the day before, and then you want to predict it tomorrow. Is it 70? Is it 71? Is it 80? So you want to get a number. So getting a number, another very famous example is actually like the market trend, like for stocks, or even like um, home price, for example. You want to know what this home could be priced for. How much would this home be priced at? And this is a very famous worksheet. Like if you are starting with machine learning, it's a very good exercise to perform. And you see like the location of the house, the size of the house, how many bedrooms, how many bathrooms, does it have a backyard or not? All these details together, and then you try to predict what could be the price of this house. This would be a regression problem. But again, for both cases, you give the model label data, you give it the answer. So for the house price example, you would give the model a lot of houses and give the price. So this house, it has 3 bedroom, 2 bathroom, and it's 100,000, for example. And then this other room, it has 10 bedrooms and it's very large. It has a backyard and it's 1 million, right? So you give the model a lot of houses and a lot of prices, and then you hope you have a new house in the market. You tell, like, you give it to the model, and then the model can predict the price of this house. This is the concept. We have a question here. Is the ultimate aim of machine learning is to purely unsupervised, where the machine is autonomous doing tasks without human interaction or supervision, or will there always be human supervision of all ML processes? That's a very good question. I would say the answer, there is no specific uh, target. It's all about getting the job done. If our problem, it's again, always think of machine learning as a tool. You have a problem, this is the tool you want to use to solve the problem. This is all what we care about. If our problem will be solved by this supervised learning, then we are fine. If our problem, for example, you are out, like you want to some humanoid robots that go out into the like uh, places of hazard, like to have a volcano or you have an earthquake, and you want the robot to go out and save people. So your problem in this case needs an unsupervised robot to handle, right? You can train it at the beginning supervised, and then you try to give it some scenarios to figure it out unsupervised. But it's all about your ultimate goal. Machine learning, robots, AI, we have to think of it always as a tool to help us achieve our goal. So if whatever solves our problem, whatever gets us to our goal, should be utilized. I keep notification somebody's like raising his hand or something, but I'm not sure where does this show. So please write in the Q&A if you have any questions. Um, Alrighty. So moving forward, um, as explained, these are the two main types, the classification and regression. If you look at this picture to really um, uh, explain this in a very practical manner. So this is the classification. We have a certain problem, like so the this green circles are one group, like these are spam emails, and these blue ones are the non-spam, and we need the machine learning algorithm to be able to differentiate between the two, separate the two, classify the two. This is what we call like I need this line. So machine learning basically is drawing this line. This is what we call the hyperplane. So for a future, I get a new email and I have some parameter here that I see the value of, and then I have some parameter here and I see the value of. And then maybe the email is here, then I say, okay, this email is a spam, or the email ends up here. So I say, no, it's not a spam, right? And you can see this will never be 100% accurate. You can see here with the spam, some legitimate emails, some good emails are marked as spam. They are grouped or classified with the spam, and some other spam emails are actually classified as good emails. And this happens with us, right? You open your spam folder, oh, I have been waiting for this email, but it was classified as spam, and vice versa. There is a spam email, and you find it in your inbox rather than in the spam folder. So it's working. Most of the spam are in the spam, and most of the good emails are in the good emails, as we can see here. But um, it can make mistake and it will make mistake. That's why additional training data is always useful. Now the very famous question here is like, okay, so what is this? What is the x-axis and what is the y-axis, right? This is what? And the answer is that it depends on the model. How did we train the model? Maybe we train the model on only two parameters, right? How many characters in the email, and maybe if the address of the email is at Gmail. Any example, and then this is how we attribute. But in reality, we don't have only have two parameters or two attributes or two features. We have so many, and then we can combine them together or do what we call like have PCA, like we have a new parameter based on multiple parameters. So this is what happens inside the machine learning model, a parameter that gets mixed with another parameter and so on, and then we finally have a specific parameter that we use for the classification. When it comes to the regression, again, you can see it's not about classifying or separating points into two groups. It's about having this trend line. I want to regret. So I tell you tomorrow I have this parameter and this parameter. What would be the next parameter? Or for the houses, I tell you the house is it has this size like this foot square, and it has this number of bedrooms, for example. So tell me the price. So I give you a new house that's at a different price, at a different number of rooms, and then you tell me the price. So the regression is about finding the trend so that I can use the model to predict any new house, what will be its price. So you can see the difference between classification, separating things into groups, or regression, which is finding the trend to be able to predict anything along this trend. So this is the summary of the supervised learning. When it comes to unsupervised learning, it's basically it's not a labeled dataset, right? Very simple. So it's using an unlabeled dataset, right? And there is no supervision, and we keep the algorithm trying to figure out what to do with the data, what similarities there is. Maybe it's unsorted, so we try to sort it, find patterns within the data, um, get some insights in the data that we cannot see with our naked eye, right? You have so many data, and then the model can say, oh, these data are all in one group. These pumps are all in one group, so maybe these are all gonna fail soon. But we didn't see the pattern. Why all the pumps are treated together? So this is how we treat it. Like we have the clustering. So clustering is the technique we refer to grouping objects together. right? On parameters such as similarities or differences between them. Maybe you have an e-commerce website, you are selling things online, and you have your customers, and you don't have a specific way to classify your customers. These are customers that most probably will buy from me in the future. These are customers that actually will not buy from me again. These are customers that can buy if I give them a promotion. This is very hard to know, right? How do you classify these parameters? How do you group them together? So if you have, if you know this is these are good customers and these are bad customers, then you have labeled, and then you can make it as a classification problem. You can make it as a supervised learning. But you don't have that. You don't have a label to say this is a good customer, this is a bad customer. Still, you are grouping them. You are sorting them into groups, which is very similar to what we did here, what we did in the supervised. But in this case, I don't have label data. I don't have a way to sort some customers in one group and another customer in another group. But if I'm able to do so, this is very helpful for me, right? I can know which customers to target. They will properly purchase from me. Which customers to not waste time and money on. These customers are no longer will buy from me. Or what customers I should give them some code or promotions. So these are good customers. So I don't have a way to tell, but I want to achieve this clustering, and this is where unsupervised come in. I just give the model all the data of my customers. I didn't tell the model anything, which is which. It's unlabeled data, but hopefully the model will be able to cluster them and help me to deal with my customers in a better way. Another use case for the unsupervised is what we call association. So this refers to identifying typical relations between variables in a large data set. You have so many variables, for example, and then you can give all the data to the machine learning, and the machine model will come back and okay, all these variables are the same. It's actually the same. The total number of orders for the client, or the total number of the total amount the customer spent, like some variables, they are very similar. They will have the same effect on your model, so you can associate them together or deal with them in the same way. So based on that, somebody might ask, so what would be the difference again between classification and clustering? I'll give you a second if you can answer this. Like, think about this for a second. What would be difference? I just want in one or two words the difference between classification and clustering, because I know to a lot of people they seem to be almost the same thing. But I want to hear from you now. Is it clear what is the difference between them or not? The label. Thank you, Hagar. That's a very good summary. Any other one? Like, what would be one word to summarize that? One or two words? Like, we have Hagar so far. Okay, I'll give you a couple more seconds before I stop that. Okay, classification is supervised, I guess, and clustering is not. Clusters are groups, similar or not. Classification is something uncommon. Okay, very good. Thank you all for your answers. So I will like revisit them quickly. Uh, my chat is disabled. That's fine. Yeah, please post in the QA, and I will mark you as read. So, Hagar, thank you. It's exactly the label. So, if we have a label, that means it's a supervised. Like I'm telling the model what is this, so the model can learn. So it's this is the really the core part. So that's correct. Thank you. Well, classification is supervised, and that's correct as well. So classification, I have the label, so I'm supervising the model. I'm telling the model what to learn from this data. So that's also correct. Clusters are groups similar or not. Classification is something in common. I'm not sure that's very accurate. Clusters are again they are similar, but we are like maybe similar in a way that we cannot see easily. So that's, but at the end of the day, both clustering and classifications will group things together. I have a photo here that I will share with you shortly that will make it very clear. And this is why I asked this question first, so that in the future you don't forget, because this is very easy actually to forget. So this is classification, this is clustering. In both cases, as you can see, we have groups, right? So now I had this original data, but then now I have this one group, one group, one group. So that the end result is that I have three groups after I'm done with classification. But actually, for clustering, it seems like it's the same thing, right? By the end of the day, I have three groups for my data. Now, the core difference here is these symbols. So for the classification, it's supervised. So I'm telling the model, these are all circles, these are all stars, and these are all plus signs, right? So the model classifies them, and now I know these are all stars, these are all circles, and these are all the stars. Sorry. When it comes to clustering, we have a group, but for me, they are all the same thing, right? These are all my customers, right? So I didn't tell it, are these circles and these stars? No, I give the model all similar. I give the model just customers, just circles. But here I give the model three different things. I told the model these are circles, these are stars, and so on. But here I just gave the model all my customers, and the model did the clustering for me. Okay, all these customers they are in one group. They are very similar. Deal with them in the same way. That's it. Like clustering them, but I don't know, are these like, what are the characteristics? I don't know. But these customers are similar. They are grouped together. They are clustered together. Deal with them the same way. I have some more answers. The classification has one identifier, cluster as association. Again, not necessarily like we can see here. We have three different identifiers for the classification. Maybe you mean something else by the identifier, but thank you. Predicted and unpredicted. Thank you, Imad. I'm not sure what you mean by the predicted and unpredicted. Maybe you mean that I know beforehand what the types are, which is correct. If that's you mean, that you are totally right. Thank you. Classification, categorical, clustering, grouping. Again, I believe you got all the concept because your answers are all in the same direction. The use of the exact words is what might be sometimes tricky, because yeah, when we use the word categorical or grouping, we might mean different things. But yeah, as the last answer here, that's totally the main difference is the labeled and unlabeled, and that's totally correct. That's why this is supervised. We have label, we are telling the model what these are, and we have the unsupervised, which we don't know basically. To wrap this section up, let's quickly go through the semi-supervised. As you said, it's mostly learning comprised of characteristics of both supervised and unsupervised. So it's a combination of labeled and unlabeled, trying to make some compromises. Some of the drawbacks of one method is overcome by using the other one, and vice versa. It's just combining both to have hopefully a better result. And finally, we have the reinforcement learning. And this is becoming more and more used in different fashions. But the concept here is that you give the model is learning by try and error. And you can definitely say, okay, this is the whole machine learning, right? For the whole machine learning, we give the model data and he keeps trying, and that's correct. But the idea here is that we don't have a preset defined of data. We don't have labeled data. And the best way to really understand this is thinking of a video game. That's the easiest, that's the most straightforward thing. Like you have a video game, and you want the model to be able to play the video game. What do you teach the model? Nothing. You just give the model the video game, and the model tries to move right and then dies, right? Then okay, I shouldn't move right, I should move left, and then the score goes high, and then moves right again and then dies. Okay, so left is good. So the model starts to move left and then it dies. Oh, and then it starts, maybe I need to jump. So it's complete try and error, no label data. The model just keeps trying, and then we have what we call the reward system. So if the score is going high, then the model believes, okay, I'm doing something good, so it keeps doing it. If the score is going low or not improving, or like goes zero, meaning that it's dead, that means okay, I'm doing something bad. It's not very applicable here, but it's very, very important. This is how the actual humanoid robots, like a lot of the practical machine learning applications, are based on the reinforcement learning. But for our use cases for the oil and gas, it's not as applicable as other franchise. But it's one of the very important, I would say, domains for the machine learning. So just as a summary here, these are what we went through the machine learning. We have the unsupervised, we have the clustering, which we talked about. Sorry, the supervised. We have the classification and regression, and these are some examples. The image classification, one example we talked about. So this image will have a lot of, like, summarize everything. If you get lost, confused, this image should be your way to go. We have the image classification: is it cat or dog? Or maybe identity fraud detection, like spam or not spam. Customer retention, like is this customer is staying with me or not? You see the same customer example. One, we said it's unsupervised. I know nothing about this customer. Just go and cluster them for me. You see, it's called customer segmentation. But for customer retention, I can have a list of customers. These are all the customers who are left the company. They left my website, they never purchase from me again, and these are the customers who are coming back and purchasing. And I want to classify, when I get a new customer, will this customer continue with me or not? So this difference between having a specific label for the customer made this a classification problem. But if I just have a list of customers and I don't know how to cluster them or segment them for social media marketing, for any type of marketing or business analysis. So we call this customer segmentation. It's unsupervised. I just give the model all my customers. When it comes to regression, as we said, like market forecast, population growth, weather forecast, estimation life, like probably how long this will person live based on these factors of health or whatever. The same example we said about the market price and so on. All of these under the supervised. For the unsupervised, we have the clustering, as we talked about, for the marketing, for customer segmentation, recommendation systems, for like Facebook algorithm and this kind of thing, like just how I would classify this group of users, what they will like. Mostly, this is an unsupervised problem. And then the association, or the what we call dimensionality reduction, which means multiple parameters meaning the same thing. Like the number of orders is the same thing as the total amount of money that my customer has paid, right? Because they say, both of them say, okay, is it a customer who purchased from you or a lot or does not? So this is what we call dimensionality reduction. And then finally, the reinforcement learning. Of course, the semi-supervised is just a combination of these two, so nothing special. And then the reinforcement learning, as we said, like real-time decisions or gaming, the game AI, the robot navigation. The robot tries to walk, it falls, tries again, it falls until it's able to walk. Just keeps trying. There is no training data per se. So that's the first section, the core concepts of machine learning. As you said, like we have the three sections. We finished with the first section. We will go quickly with the second section with the case studies that you requested last time. Some of the papers that I'll share with you in these three different categories. And then we will go finally with our challenge and start working on it together. So any questions? I'll give you a couple of minutes to post any questions you have before we move on. The floor is yours. So while we are doing this, this is what I shared with you earlier. I believe you can see that, or I hope. Yes, you should be. So this is what we shared, like to have this session a little bit more interactive. We received 10 responses of what we liked of last meeting. Very clear. Thank you. Thank you, Arnoldo. Is reinforcement learning, you said there is no data for training. How? So the idea, Hagar, is that you again we don't identify training data for the model, but we identify some rules, meaning the reward system and the target or the objective function. Again, take the playing a video game as an example. This is the best example you can understand this. You want the model to try to play a game and win the game. What data do you give the model? Right? There is no specific data. You say, okay, when you move right, that's what. Like there is no specific data, there is no specific association. You just give the model the target. Your target is to get the highest score possible. That's the target. And then the reward, if you the score goes higher, you get a reward. Like that's good, keep doing that. If your score goes lower, that's bad, don't do this. And then the model start to try everything, try to jump, just to jump in the place, and then the score is not increasing. So okay, that doesn't seem to be good. It tries to move right, tries to move left, and it keeps exploring, keeps trying, keeps trying. So this is why we call reinforcement. So moves right, takes whatever something power up, so the score goes high. Okay, that's good. Do that. So then the models remembers whenever I see this icon, whenever I see this power up, I wanna eat it. I wanna take it because this is good. This is good for me. We didn't train the model. We didn't tell the model to specifically take this thing, but the model figured out on its own by the set of rules that we had. The rules are try to get a high score, right? And if you get the high score, keep doing the same thing that gives you the high score. So now the model learned that this power up icon, this booster icon is very good. I will always take it, but we didn't teach the model that. We didn't have a labeled data set to tell the model that. It just figured out based on the rules that we have. But great question. Thank you. Sorry to draw you back. What is the difference between AI and ML? This is for clarity. Thank you. So again, the AI, you said the AI is a general umbrella. Anything that's smart, artificial intelligence. And some of the stuff that we have is not necessarily machine learning, like the machine is not explicitly learning something, but it's a smart. It's doing something smart in general. This is the concept. Like as we said, like you have a program that can execute any like have a sense or a reason or if do this do that. So the computer does something on its own, right? If I have a program that says, okay, if I press this line, do this, or like the it's a smart, like it's doing something on its own, but I programmed it to do so. But when it comes to the machine learning, that's deeper. The machine can learn, so it has set of rules that we didn't explicitly add. So it's a deeper level of learning, and the deep learning is even deeper, and then the generative AI, as we covered last time. Thank you. Okay, let's go back through the list. Thank you for the responses. This is from last time. I'm just having this here because I want to utilize this. I give you some interactivity, and then you can answer the question. So what we like from last meeting or this meeting, opportunities for the onward, write code together in real time. We'll start this, the interactive, learn about LI, machine learning, a lot of topics, discussion about oil and gas, learn ML. Examples are so clear and the concept, thank you so much. New topic, very good. I'm really glad. Thank you for the positive feedback. Let's go back. I will close this. And then we are ready to start the second phase. So no more PowerPoint here. So let me close the PowerPoint and start to share my screen with this. What? With this. Okay, so this is I have three. I will share the articles with you, the links with each one that I open. So this is the 3 points that you asked one. We were about the government and regularity, how the AI is affecting that, about the regulations. And then we have the second one about the pipelines. We have this question. And then the third one, we will talk about the gas flow rates prediction using the shock line or the shocks in the wellhead. This also one of the questions that was asked, for example. Again, I'm not going through these in details because it's plain English. I would love to give you the opportunity to go through them and maybe we can discuss next time if you have questions. But the whole idea is that there are three considerations when it comes to AI for the regulations. Understand the unique capabilities, meaning what the AI can add to the regulations. And the core word here is what we talk about NLP, the natural language processing. Like the AI now is can understand the meaning of English. English is not just a bunch of letters anymore. It can understand the meaning of this English and then be able to adapt this. And this the next step, adapt to the business process and to the AI. And this summarizes all what AI can improve the effectiveness and the efficiency. So predictive public sentiment, like if we have a new regulation, what the public reaction to, does the public like this or not? So AI can go capture information from Twitter, from social media about this regulation using specific hashtags or whatever, and then can, okay, the public really love this or not, or it may be even through surveys. If you have a survey and then you ask people to really type what they like or what they don't like, this can take forever for anybody to review. But now you can give this to machine learning and then can read all the feedback and tell you, okay, people are really liking this or not. Of course, initial draft of regulations, you have a new regulation, you can have the AI write the first draft. So this will make things a little bit faster. Generating responses for approval or rejections. What is the best way to draft this? And then other efficiency improving, meaning things that it's already being done but can be still improved, like detecting fraud. We already talked about this. Regularity performance, like perform, like track if the dashboard is doing fine. Analyzing and summarizing input, all of these things that it's being done but it can be improved. So this is, I would stop here. Like this is the summary. When we talked last time and we had the discussion, how can AI be utilized in the regulation front? I think this is useful to be looked at. And again, I shared the article with you to really go into depth if you are interested in this topic. But I don't want to waste everybody's time if this is not something that interests you. The second article here, again, I'm sharing the link. This is for the corrosion, and this is actually a review. When it comes to publishing, These are scientific paper, but when in the scientific paper world, when we say something is a review paper, meaning that it doesn't have something new in itself, but it means that it covers everything, or as much as whoever wrote the paper can cover about people who did stuff. So this paper is very good. Like if you ask a question, what did people do when it comes to utilizing machine learning in gas pipelines, corrosion and cracking and failure, you can just come to this paper, right? Because this paper, what it does, again, a heavy reading if you are really interested, but it's very, very informative. But the core part that I'm scrolling to is here. Sorry, I skipped it here. You can see what parameters that they was able to identify through the machine learning, and every different paper did different thing. So a lot of papers, 27 of the papers, were just analyzing the corrosion rate, right? So you can predict how critical this will affect your pipeline. Some predicted the corrosion potential. Will this have corrosion or not? Leakage identification, corrosion failure, pitting depth. All of these are terminology in the corrosion world. I believe you should have studied like metallurgy or something. But this is all detected using machine learning, like artificial neural networks. So they use that. Let me zoom a little bit. They use that to identify the problem and be able to predict this. And then it tells you, okay, this paper did this and this paper. So it gives all the papers, all the research that focus on a certain problem. So you can see here from the table how many papers they covered almost 171 papers. So instead of you going reading 171 papers about the machine learning and the corrosion, they did this for you, summarize it, and then you can really focus on what you wanna. And this is something I highly recommend. Like when you learning about some new topic, you go to a review paper. The word review is your keyword. So somebody who's reviewing all the work, all the research work that was done on a certain topic, and they summarize it for you. So that's very, very useful. Another one in the same area which I really liked. Again, it's a systematic review. So see, I'm giving you the review papers, not a specific paper, because there are hundreds of papers. But the really useful stuff is to have this review paper as your start point. It's a summary of what everybody has done up to when? Up to July 2023. So up to last year, right? For up to last year, what has everybody did in the pipeline failure prediction through machine learning, right? Fantastic. So this is very, very useful for you. Again, let me zoom a little bit. And again, very in-depth, like you can see my scroll bar here, very in-depth. Of course, we are not going through it in detail, but the rate of papers, you can see recently the number of papers jumped a lot, right? Nobody, like very few people, one or two people were talking about this in 2013, but 2020, 2022, you have more than 25 papers. Countries, don't worry about that. So our objective is here. Again, a huge paper, but what I'm showing you, if you're really interested, want to study this, this could be a project for you. The summary of the studies, a prediction of oil and gas pipeline failures. It tells you every paper, what did they study, the input parameters and the output. So this paper used the flow rate, the velocity, the pressure and temperature, so four parameters to predict what? To detect the leak location and leak size. Fantastic. So you go to this paper. How did they do it? Learn from it. What methodology did you use, and so on. And for every single one, this is why this is so valuable. It's this one summarizes if you read the whole paper. So this is very. If you are really interested in the application of oil and gas, machine learning in the oil and gas industry, you have really to learn how to search for such. How to find the review papers that interest you, and it will summarize a lot of information for you, like years of work is in just in this one page. You read it, you understand it, you pick it, you can see we go on and on. These people using the flow rate and the pressure, they detected the pipeline leakage. Some of them they use the pH value and predicted the CO2 corrosion rate. and the list is, I wouldn't say endless, but pretty large. So this is again different strategies of what they used, different algorithm. One of the new frameworks, explaining the framework, and then another summary when they use hybrid machine learning algorithm. So the previous table was only for artificial neural network. This table was for hybrid machine learning techniques. So for them, they use like pipe diameter, radius of curvature, steel hardness, a lot of variables, but they predict the erosion rate very accurately. These they used like some safety effects, and they were able to predict the failure criticality and so on. Every single research, what they detect and what variables they had to be able to predict that. So if I ask you, so give me examples of, that's why I didn't answer these questions last time. Like, what is a variable of detecting pipeline failure in machine, like using machine learning in the oil and gas? It's infinity, right? There is a lot. What exactly do you want? You can predict the internal corrosion rates of oil pipelines if you use the acid number of the oils, the sulfur percentage in the crude, the temperature, the pressure, and the velocity of the oil inside the pipeline. If you have this, you should be able to predict that using a method using the PSO SVM. SVM is like support vector machine, is kind of machine learning algorithm. So you can get the real-time detection leak if you have the pressure, the flow rate, and the temperature, and so on. So this is the second paper, fantastic one for this area. Again, you asked for it, so thank you for bringing this to everybody's attention. And the link is in the chat. It should be accessible. Uh, and best of luck. The last one that we can go through is about that wellhead choke in gas condensate fields. This field actually is not accessible freely. I have access. I downloaded it. Let me open the PDF quickly with you to show you what it has very quickly. Again, the examples are unlimited, but I'm giving you real real time, like real fields from publications, um, very recent publications, like new ones, recently published. This one is published when? This one 2021, the other ones are 2023 and the 2024, very recent publications. This is the one for the choke condensate. So again, this is one of the very, very good things to look at in a paper. What is their procedure, their methodology? So they have a very clear steps: collect the data, store the data, normalize the data. We will learn about this. Detect the outliers. If you remember our typical steps, this is an expanded version of it. Calculate all the errors, divide the data into training and testing. We talked about that. And then compare multiple machine learning algorithms. You don't know which one will work the best, right? Even if you know this is a classification problem, this is supervised classification, you have tens of algorithms, machine learning algorithms that can do this for you. So you would try different ones, you'll derive them with different parameters. And this is why in the challenge that we are working on, you can see leaderboard with huge difference. All of them are good people, they knowledgeable, they know what they are doing, but they are not getting the same results because everyone is trying different algorithm, everyone is trying different parameters for the algorithm, everyone is processing the data in a different way. That's why this is challenging, but also exciting and fun. Again, this is very, very similar to what we discussed today. Input data, sort the data, classify between training and testing. If it works, otherwise go back. The same structure with different methodologies, and then they have their data points and where they're coming from, and the summary of their data points, the temperature range, the different fields they got the data from, and then their actual prediction, the empirical CDF, as in terms of the temperature. You can see between you can see in the legend between their practical data and their fitting data, they have a very, very good matching, very low standard deviation. So very good paper and to in the choke line optimization with the oil and head. Again, like I think I shared the link with you. for the actual paper. I know it's not fully accessible. I'm not sure if maybe Mayar can share the PDF later with you, but if you can access it, I'm still sharing the link with you. It can be very useful if you are interested in this specific domain. But I hope you get the idea, right? This is the purpose here, is that you broaden your knowledge. How can the machine learning be used? Is it this a question? Oh my God, yeah, people did this and did that, and I read about this and I saw this paper. The opportunities are unlimited, and it gets you thinking and gets you excited to really learn, and hopefully next you implement this in your own problem in your own field. How can one build a machine learning algorithm? So building a machine learning algorithm, we are not going there. So I had a quote from my professor during my masters. I really love this quote. He's telling me, we are not computer scientists, we are engineers. We are not building the car, we are learning how to ride the car. You don't have to really know how to build a car, how to build a motor and all the transmission. You might have a good idea how it works, right? That's fine. So that if there is a little problem you can handle. But we are not here to build a car. We are here to use the car, drive the car, and get to our destination. It's a tool. And this is exactly the same thing I'm saying here. So we are not building the machine learning algorithm. We are using existing machine learning algorithms to solve our problems. And this is a completely different thing. How the model from itself is constructed, what is the math behind it. I'm not a mathematician. We are not covering this here. You can go study this. It's fun, but it's not. There is no direct relation between doing this and or actually using this. Like 99% of people driving cars cannot make the car. They don't really know 100% how the car works, but they know how to use it, how to drive it, what are the transportation rules, and utilize the car. And this is what we are trying to do. Understand machine learning in general, understand the algorithm, not build the algorithm from scratch, but actually use them to our benefit, which is to solve problems. I hope this answered your questions. And now, in the last 30 minutes, we are in the third part of the lecture today, is actually practical, hands-on, using the like looking at the onward challenge, so that hopefully, if you start doing it yourself at home, you have a good idea. Like I give you a head start, and we try to solve it together. So, any questions before we do that? Alrighty, let's go then. I believe I already shared with you the challenge, but I can share it with you again if we have new attendees today or something. Um, Here's that challenge. So very quickly, we will read the exact challenge. Like we will go through this page today. Maybe this is where we stop. Like I'm not sure how time will behave with us, but at least we need to get our hands dirty, really start discovering this. So this is the official page of the challenge. I shared it with you. You can see here. Let's like if you are new to Onward, the first thing you really want to read all this top part. First thing, this challenge is classified as time series. So we will talk about what is time series. And again, this is how we are go. While we are going through the challenge, through the code, a concept it's new, we didn't explain it, I will just jump and explain it. So this is very dynamic, as discussed last time. So this is a time series thing, we will talk about this, and it's anomaly prediction. So we want to see if some data is bad, some data is wrong. And this is if you really remember that photo we had today, you can I think you can remember. Does anybody remember where did the anomaly detection uh, reside in our charts? I leave it to you, but you will see soon. So the name of the challenge is Spot the Trend, Pattern Recognition in 1D Pressure Data. You can imagine like 1D is like linear pressure data. It's pressure versus time. It can be 2D or it can be even 3D pressure data if you are inside a reservoir. But here it's a simple challenge, just 1D pressure data. Overview. So this is the overview. It explains the challenge. Here we have the actual data of the challenge, how to download it, the size of the data, and so on. You can see here the training data is 3 GB. I know this might be challenging for some of you um, if you have low internet connection, but this is what we are dealing with. We might even cut the data to make things a little bit faster. We will see. And we have some rules here. I wouldn't worry about the rules much. Leaderboard, meaning which teams are at what level, basically who is achieving the highest scores. But this is not the final score. The final score happens after um, the 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 challenge, because the team will take the top 10 and they will run this against will run their models against other data set, just to make sure nobody cheated. Some people can like cheat the system, really understand how the system is evaluating the data and play with the training data to get high results, but the model is not actually good. And we'll learn about this, something called overfitting. You might be getting a very good result, but when you actually use a model, it doesn't behave well, right? So that means the model just memorized the data. It didn't really understand the data or understand the relationship between the data. It just memorized the data. And this is not what we want. And then we have discussion. This is people asking questions in real time. Hopefully, people are answering. So um, this is the discussion forum, and then the team, your team. Here it's my team. I'm the only one. And finally, the submissions. If I submitted something before, what is the score? What is the previous score, the new score? Of course, I didn't work on this. Like we should be working on it together. So I still don't have any submissions. So let's start. Overview. What is this a challenge about? I read it out loud together, and then hopefully explain if something is not clear. And please utilize the Q&A to post anything that's not clear to you. Welcome to an exciting trip into the world of oil and gas production. Our journey takes us deep beneath the Earth's surface, where we collect bottom hole pressure. So you should know what bottom hole pressure is. It's the pressure that we measure at the bottom of the well, in front of the, like, what we call the face sand, or the sand face, sorry. Like it's in front of the reservoir inside the well bore. The data set for this challenge is a wealth of information, poised to reveal insights into the dynamics of energy production. Just like the Ghosts of Holiday Past challenge, this is another challenge that Onward had. This challenge is focused on time series data. These bottom hole pressure data are one of the keys to understanding the intricacies of energy production. This data hold information about patterns, anomalies, and potential opportunities. That's exactly what we're saying. Like you have information embedded in the data. For us, it might see some simple data, but for those of you, if you studied like maybe well testing, you really realize just this curve, this rate of a change, how sharp this line is. All of these mean so many things. Like it tells us about the reservoir boundaries, it tells us about the type of the fluid. So some of this stuff we already know from well testing, from solving the wave equation and all this fun stuff. But maybe some of it is really hidden. We didn't figure it out. So let's see if machine learning can really help us even discover more. And this is exactly what it says. Like we have some hidden treasures inside this data that we want to extract and learn. A lot of opportunities, as they put it. By deciphering the intricacies of bottom hole pressure, you will gain invaluable insights that allow optimization, improved safety, and increased efficiencies. For this challenge, we have provided you with a set of 1D bottom hole pressure time series data. So this is the type of data we have. It's a time series, meaning for each pressure, there's time associated with it. We measure this pressure at this time. We measure this pressure at this time. Time is a factor. That's the meaning of time series data. It means time is a factor. If you remember our example of like the cat image and the dog image, it doesn't matter if you have cat image, dog image, cat, 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 dog, 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 cat, dog. It doesn't matter what order you give to the model, right? Because the model cares about this image is a cat, this image is a dog, period. The model does not care about the sequence. When it comes to time series, it makes all the difference, right? This point came before this point or after this point. That means is the curve declining or is the slope increasing or the slope decreasing? What is the rate at which the slope is increasing or decreasing? So this is very hard, right? This is very challenging. The order of the points, the sequence of the points, this makes the whole difference. In our classification example, it doesn't matter. And even in our regression problem, like what is the price of the house? Okay, it's this house, number of rooms, number of bathrooms, the square footage. That's it. So what order is the houses are given to the model doesn't matter. The model looks at them one by one, just cares about one photo, about one house at a time. But here in the time series, it's a much higher, much tougher challenge. The sequence, the order of the data points makes a lot of difference. It's when did we measure these data points? What is the sequence and order of them makes a difference. That's why this is a harder challenge, as we explained earlier. I know some of you suggested we go with an easier one, but really it doesn't matter because our code, the way that we process the data will be very generic. Like we are not competing to win the top spot of this challenge. It's just the awareness, like there's something like this out there. Please go, please learn, please explore. And any barrier that you think, no, this is too advanced, I cannot submit anything. We try to break this barrier together by really doing something live and submit. As you saw, I didn't submit anything yet. So the plan is to do this together, submit it, and hopefully this opens opportunities for you for the future. Um, One question here: how do I get access to the web page? For this web page, it's a free sign up. Like if I open this in an incognito window, what happens? I click on join, and then it asks me to log in, and then I register. So you can just sign up. This should work. I'm not sure if this, let me try again for the sign up, register. This is just a sign up link, like click on register or click on sign up, and you should be able, it's free, just an email and password, and you should be in. Please try and update me if you're facing any problems. For this challenge, we provided you with 1D, we said that, for oil and gas production and water injection. So we have two um, information going in. We have a pressure and we have production and water injection going. Your task is to predict if a well is flowing or not, giving the bottom hole pressure. Very simple, theoretically. We just want to know is the well will be flowing, like we have um, uh, net positive flow or not. It's not flowing based on the value of the bottom hole pressure that we have. Okay, let's learn about the background. So the data for this challenge are bottom hole pressure time series from oil and gas wells. Bottom hole pressure are key metrics in energy production as they document the pressure present deep within the Earth's subsurface reservoirs. These pressures in turn help characterize the interactions between rock formations and fluids moving within them. Of course, this challenge, like computer scientists and other non-petroleum engineer peoples will be like our other non-petroleum engineer individuals will be looking at it and they don't understand. Like maybe as petroleum engineers, we have much deeper knowledge what's going on, what's the bottom hole reservoir pressure. But here you can see they are explaining, even so non-petroleum engineers or reservoir engineers can really understand what's going on. By monitoring and analyzing bottom hole pressures, we can optimize well design, production rates, and maximize the fluid recovery from each well. Understanding and monitoring these pressures also help us detect for wellbore instability or formation damage. This helps us safeguard personnel, protect environment, and mitigate potential hazards. The data contains measurements of the pressure at the bottom of each well in 1 minute interval. So this is the time series. So we get the data in 1 minute. So 100, 101, 102, 103. What is the pressure reading at each one of these data points? That's 1 minute intervals. These data show how the pressure in each well changes when they are opened and closed, flowing and shut in respectively over time. So this is like see figure one. So this is figure one, pressure plot showing different patterns in pressure as well shut in. So this is what we can see here. You can read the pressure, right, in blue. So this is our pressure, and here you can see the gas rates production, and you can see the measured bottom hole pressure, and you can see the calculated bottom hole pressure, right? So what is actually measured and what is predicted or calculated based on that. Um, for producing wells, pressures generally rise while shut in and decrease while flowing. For injection wells, the opposite is true. Pressure generally rise while injecting and decrease while shut in. And this makes perfect sense for us and easy to understand for us as petroleum engineers. Due to sensor issues, some of the data in the time series are erroneous or missing. And this is very expecting. Like we have to this is very, very core when it comes to machine learning and data science. Always question the data. The data is very bad by default. Why? It's coming from underground, very high pressure, very high temperature, sensors, thousands of feet down in the ground. So don't trust the data. Question the data. Maybe this data point is wrong. The maybe the battery ran out and some of the data are missing, and so on and so forth. So always question the data, and they are highlighting this here. This challenge asks you to build a model to predict if a well is flowing or shut in. The model should take into account the shape of the time series. And this is what I'm telling you, that this shape makes a difference, like the curve. But if we are dealing with classification problem, like cats and dogs, we don't worry about it. Like every data point is its own thing, it's a standalone. But here, the sequence, the series of the data points is is important, and that's why we call it a time series challenge. Like these data together is one unit, right? Not every data point is one unit alone. All these data together is one unit because they define the shape, they define the rate. Like it means something. The sequence of the data has a meaning. And the pressure values over time. Keep in mind that we consider producing and injecting wells, so increase or decrease must be identified depending on the case. So when you are dealing with the well or the data, you have to pay attention. Are you dealing with production or are you dealing with injection? Because the trend will be basically opposite or vice versa. What data do we have? The dataset provided for you for this challenge consists of time series bottom hole pressures for 200 oil and gas wells. They can correspond to producing or injecting wells. So it can be this or that. So shut-ins correspond to increases or decreases depending on the case. Each well has a unique profile that represents the geology, completions, and operations of the well. Figure 2 shows two of these wells. So we have two wells here. It shows two of these wells with associated flowing and shut-in labels. Use these labels to build your predictive model. So, quick question: is this supervised or unsupervised? Very direct question. However, be cautious of overfitting, as we just mentioned this word before, and we can expand on the overfitting next time. It's supervised for sure. Thank you, because it has. I'm not sure I got the name like Olsgun. I'm not sure. Sorry if it's wrong, but thank you. It's supervised because we have the labeled, right? We have it's very used labels. Like so here, you can see it's telling us of example. You can see it telling us of the labels. So where do we see the labels? Of course, we'll see the labels when you open the data, but you can see from the colors that the data is labeled accordingly with blue or red. And we will see this with the data when you open the data, but we know we have labels. Dr. Aloush, the link you dropped is not highlighted. Not sure what highlighted means. I'm sorry. If you can explain, please. However, be cautious of overfitting. We will explain overfitting next class, as the holdout data for this challenge will be more diverse than what is in the train and test dataset. And this is what I said. Some people cheat. They take even the test dataset they train the model on, so they get very, very high score, but actually the model is overfitting. So when they take this and test the model on some other data that you never saw, maybe your model performed very bad. And that's why in the leaderboard, the person that's now on the top doesn't mean he is the top in the competition. He already won the competition. No. They will take his model, train it on other dataset that he never saw to make sure his model is really good, not just memorizing the data. And based on that test that they will do, then they will determine the final result. One of the goals of this challenge is to create a generalizable model. Like a model can be generalized, can be used on anything, that can be deployed in many different data conditions, right? So don't do a model that's just about this data. Try to get something smart, something general, so that we can use it on other data sets or other data conditions. So this is the data set here. The evaluation, how to evaluate the model. This is too early for us, to be honest. Like maybe in the last session when we try to submit something, we can revisit this, explain. Hopefully you will have a better understanding by then of what's going on. So I will skip this part, and then the final evaluation. Again, this is when you are really serious, like you are really winning. What they will take, what you should submit. They will take your code, they will run it. As I said, they will submit an algorithm on AWS. It will take 24 hours. Like a lot of the details about the actual competition, the actual prizes, when the competition ends officially, and so on. So this is the competition. I think we are very ready. I'm excited to really look at the data with you, explore this. So what do we do? The first step is actually go to data, right? And our target is actually to get 70%. That's our target. You can see here it says starter baseline 70%. You can see people already, a lot of like people are getting lower than that, but with the code that they gave us, we should be able to get the 70% or maybe a little bit higher. And this is very good for us. Like this is our target with this very short time. Hopefully we can do it in the short time. So for that, we don't worry about writing our own code. We just need to use the code that they have. But this is not easy, like to get the code to run properly, to load all the data they have. Like we have a lot of work to do to just get to the 70% and have something ready for us to actually hit the submit button and upload. So it's a lot of work to just use all the information that they gave us without improving on it, just the baseline. So to start, we will click on this line, open in Colab. So Colab is an amazing thing that you have always utilized and learn about. Colab is a computer in the cloud. It's provided by Google. You can see here it's a part of Google search on that address bar. And Google gives you a computer for free in the cloud to run the code. This is very generous of Google. Of course, the free version is very limited. You can pay to have a much like fancier computer, but it still works. And this is what we will try to use and see how it goes. So this is the notebook. Again, you can read that. It's exactly like very similar to what we already read. You can read that, and this is the how the code is. You can see here very large code, very explained, very good. We just need to run it, understand it together, and submit based on it. So the first step, just something I wanna do with you, is to come here and click run. This what does this do? Yeah, it actually if you look at the bottom top here, like the top right, it says connecting. So Google is going out to Google server, reserving a computer for you and giving it to you to start running your code. So now I have a computer, and this is the specs of the computer. I have 100 gigabytes on the disk, I have 12 gigabytes of RAM, and my computer is ready for me to use. Now, to use this computer, or to be able to run this Python code that we will explain, if I try to run this, you will see I have some errors, right? Why? Because I need to install some. This is a brand new computer now, right? We just got ourselves a brand new computer. Congratulations. This computer, we need some program, some software to run. The code, the language that we are using is called Python. So we are using Python. This is what we call IPYNB. This is Interactive Python Notebook. So this is Python code, but it's in a fancy way where you split your code into small chunks and you run every chunk separately. Run this chunk of code for me. Thank you. Please run this chunk of code. Thank you. And so on. So you take it step by step. You can understand every chunk. You can check the output for every chunk. So for you to get started to play with this, you click on Open in Colab. You come here, remove the sign. That means, because this sign means it's a comment, like it doesn't really execute. But if you remove it, now you can run it. You see what's happening. Now we don't have the requirements. So the code here is trying to actually install some of the libraries to be able to get the required libraries from the internet, and from what we call pip, basically. I don't want to make it complicated. So the pip is basically a place where they collect, or they reserve all the different libraries that people can use in one place, and then you can come and actually use or download these libraries and start using them. So this is the part that we need to start with. So this is not available here. So let me, instead of that, we can just stop using this library and run this code. So you can see now, if you get this check mark, that means the code is ready for you to start. Now, to actually start, this is the code, like this is the data set that they have, and we should start reading the data set. But for that, we have to really load the data and make it ready for us. I don't think we will have enough time. Unfortunately, we are at the break of the hour. So I think we are like ready to really dive in next time. We have all the knowledge, we understand the challenge, we have all the base data for us to start, so we can directly jump into this with the start of next session right away. I'm not sure, Mayar, if we have to stop here. Um, Maybe Mayar is not with us. But yeah, anyhow, I know Jupyter Notebook and Google Colab enough for ML, because some persons use Spider, VS Code. Is there any difference? There is no difference actually. This is exactly VS Code. Like if I run on VS Code next time, if my computer allows, you'll find this the same thing. Um, Google Colab just gets things faster. VS Code is actually will be running Jupyter Notebook, so it's the same thing, either on the cloud or either on your computer. So there is no big difference between the two. So we should be for our problem, we should be good. Like the challenge is when we deal with a large data set, so you have to upload the data set into your Google Drive. So this takes a little bit of time. So this is usually the challenge. But other than that, in terms of capability, we should be good. I can get focused on Jupyter Notebook or Colab. So they are, I wouldn't say they are the same thing. So Jupyter Notebook is the place where you have your code. Now, where you run it is you can run it on Colab, you can run it on VS Code, you can run it anywhere, right? It doesn't matter. So the Jupyter Notebook is the place where you type like information about your code and you write the actual code to start. So that's good. How long is it competition running for? So the competition, it has been running for a long time. It has been running for 11 weeks and it has 2 weeks left. So hopefully we will have time to have a submission before the end of the competition. I really hope so. Uh, Thanks for the clarification. Thank you so much. Alrighty, I think we have to close the Zoom meeting because I think there are other training sessions or something. We have to close before 2:30 my time. Thank you, everyone. Looking forward to a lot of coding next session. Have a good weekend. Bye bye.